myself?
Please. I think we're all set. So, second speaker for the session.
Okay, my name is Sliwa, and I'm from TU Dortmund, and I'm also talking about mobility, but from a different point of view. So I'm focusing on mobile robotic networks, and I'm also discussing the impacts of knowing how we are moving in the future on the routing decisions. So at first, I'm taking a look at the problem statement here. So this is a typical use case for us. We are using drones to explore dangerous areas, for example, an incident area and nuclear power plants. So what we do is we send these agents out there, and then they create some sort of mesh network. And then we use this mesh network, for example, for streaming video data to a base station which is outside that area. But the problem here is that you can imagine this high rate of mobility, and due to the high rate of mobility, there's a constantly changing network topology. And then we have to deal with packet loss and link failures and stuff like that. So this is really stress for the routing protocols, and we said, okay, we are the ones who are sending these agents out and we are controlling them, so why not use the knowledge we have about mobility to make intelligent routing decisions? So that's where we want to go. And my outline here is we have a task, which is exploration, for example, and we have a goal here. We want to improve our packet delivery ratio. So what we can use are the mobility algorithms, and they are considered as controlled mobility because we are controlling. And I'm going to present a meta model for OMNeT, how we can implement those kinds of mobility algorithms. And then a prediction method which uses knowledge about the mobility model in order to predict the trajectory. And then two approaches for routing which make use of this prediction in order to optimize the neighbor selection process. And to conclude that, I'm going to show a quick proof of concept evaluation of both methods. So for the mobility modeling part, there's a famous model from Reynolds, who comes from the gaming and animation industry, and he describes the mobility models for agents which travel in swarms. So this is about cooperative agents. And it consists of three elements: separation, cohesion, and alignment. And separation here means, in our context, collision avoidance. You can imagine we don't want our agents to crash and then we have another incident. So this is often modeled using forces. So if agents are quite near to each other, they use repelling forces which push them out of this direction. Famous approaches to model this are potential fields or distance-based approaches. And then the antagonist of this of separation is cohesion, which means we are using them as a network, as a mesh network, so we need some sort of minimal distance in order to have valid links. And basically this is the same if agents are separated from the swarm. We use attracting forces, and then they point towards the centroid and the agents move into this direction, and the modeling approaches are very similar here. And the last point is alignment. We understand it here as cooperative task fulfillment. So this means there's some similarity in the mobility behavior of agents which travel in a swarm, because here they are moving towards the same direction. You can see here we have multiple things which run in parallel, and this is currently not supported in OMNeT. So what we need is some sort of meta model which executes all this stuff in parallel. And luckily, Reynolds has also proposed a famous mobility model, a meta mobility model. It consists of 3 layers. Those are action selection, locomotion, steering, and locomotion. And the action selection part is somehow a global task definition. So it just defines what the goal is. So network provisioning, exploration, and stuff like that. And you can also imagine this is about agent classes, for example. So we have different types of agents. Some move and explore, and some are responsible for maintaining the network connectivity. But this is not that important for us. The real important layer is the steering layer, which forms the logical part, the action selection. This is really where we define how we can fulfill such a task. So here we have the path planning approaches, collision avoidance, swarm coherence, and those are the real mobility algorithms. And all of these steerings are implemented as classes, and then in each mobility update iteration, they generate a vector which points towards the next desired position. So we make no assumptions on if we can reach this position. It's just where we want to go. And then they generate a steering vector. And if we have multiple steerings, we assign a weight to those steerings, and then we compute the weighted mean, and yeah, we get a total vector. This is then passed to the locomotion layer. And the locomotion maps the desired vector to a vector we can really travel with respect to the physical capabilities. So this means for simulation, we are just calculating the next position. So we have to take the orientation into account and the length of the vector, because we are not, we have speed limitations. And this is also providing an abstraction layer differentiating between simulation and real vehicles. So you could basically use the same code for simulation, for the mobility algorithms, and then deploy it on real vehicles which control the motors instead of calculating the next position. And it's also abstracting the vehicle types. So you can use unmanned aerial vehicles, which can basically move in every direction, and then planes, which have to use other mobility types. So let's take a look at an example here. And we are focusing on the black UAV. So I have two steerings. One is for exploration with a lower weight, and one is for collision avoidance with a higher weight. And in the first step, we are now handling the exploration part. So we are generating an exploration steering vector, which is pointing to our mission area. And in the second step, we are then taking a look at collision avoidance. And here we see that there is some sort of conflict. We are quite near to another agent. So this is generating a vector which points in the other direction. And then we are summing those up. And with respect to the weights, we get a total vector. And then this total vector is passed through the locomotion part. And the locomotion part says, okay, this vector is great, but I cannot really travel it. I have to limit it. And this is then the vector which we're going to travel. So you can see here, those agents are moving, and then the collision avoidance is resolved. So how we can add this as a new steerings in OMNeT? So we have provided an abstract steering module. So you just create a new mobility algorithm with extend it and then add your parameters. And there is a virtual function called update, which returns a steering vector. And what you have to do is just create this function and assign a three-dimensional vector, which is your next desired travel position. And then you can just say, okay, I want to use the Reynolds mobility model, and I have these kind of steerings, and the Reynolds mobility model will take care about updating all the steerings and calculating the next positions. So I said we want to use this for mobility prediction, and as this is a bit more complex, and this has already been published in another paper, so I'm just telling the general aspects here, not the mathematical details. We have developed iterative prediction method. So we say we want to take a look at NP steps in the future. So we have a target iteration, and we have different prediction methods, which are not available in each iteration, but we want to use the method with the highest precision in each step. So let's take a look at the information which is available. So we have our current position, PY, and some sort of position history which is stored. Then we have the steering vector, which is calculated in the current iteration, and here we have a list of waypoints, and we say a waypoint is reached if we are inside those waypoint range. And what we do is, as I said, the steering vector is our desired position. We say, okay, this is already a prediction, and we cannot really be more precise than this kind of superposition. So in the first step, we are saying, okay, this is our next position. But as the calculation of the steering vector is really complex, as I said, I have multiple steerings, and they are added. this was only available in the first iteration, and we have to change our prediction method here. So what we can use, if we have waypoints, okay, we say we want to move in the waypoint direction. And then we know our vehicle is capable of moving with a certain speed, and we can compute the next positions. And then somehow we are inside this waypoint range. So what we do is we switch the direction towards the next waypoint and continue with the same procedure. And here, I said here for the example, I want to look 7 steps in the future. So here we have looked 6 steps in the future. Now we have reached a waypoint, but we don't have any more waypoints. So what we do is just extrapolation. There's a fallback mechanism. We use a defined number of calculated positions and just calculate the mean. And now we have reached the last position with which NP equals 7 here in this case. So let's take a quick look at an evaluation here. So we have modeled a GNSS position error, which means the ability to determine the vehicle's own position, which is distorted in reality. And this is here just the extrapolation. You can see, yeah, the prediction error is quite high. For GPS, we take a look more in this area, but there are different kinds of how you could determine your own position using triangulation with radio waves and stuff like that. If we now use extrapolation and add the steering vector, you can see this is a bit lower, but still very high. But if you know at waypoints, this is really low, because the waypoints are not influenced by the positioning error, and then they can act as static orientation points, and the impact of our ability to determine our own position is really, really low. So if we use this method, waypoints, and now also add the steering vector, so this is equal to the method I have shown in the example, you can see there is not really an improvement, because the precision is quite high, and yeah, it can't really be improved anymore. So what we see here, waypoints are really great if you want to do mobility prediction. Mobility-aware routing. So we have this prediction, and we want to benefit from it. So I'm presenting 2 approaches. One is predictive path planning, and we have used OLSR, because OLSR is also using path planning. And here is an example network, and if we say we want to find a route from A to E, probably one would take this one. But we, as I said, we have really high mobility here, and we don't know how this is going to behave in the future. So what we can do is we can apply our prediction method here. So then we get a predicted network topology, and we see that this link is not available anymore. So maybe it makes sense to switch our route right at the beginning already to this one. So then we have a route, and we can skip the route switch here. So what you see is this decision is a trade-off between the shortest path and stability. And our approach here for mobility-aware OSR is to choose the path which is available now and in the future, and then the shortest path. The downside is predictive path planning. We require mobility information from all network participants, and this is generating a high overhead. Another approach, which is also part of the mentioned paper, is the stigmergic approach, which is related to N colonies. And we have extended the Batman routing protocol for mobile applications and called it here Bat Mobile. And if you ask the same question here, then you can see there are multiple paths from A to E. This one, but Bat Mobile is saying now is you're asking the wrong question, because for us it's not really important to find a route. For us it's important to make a decision as which forwarder is going to forward my message. So how can we make a decision about that? And if we now add flooding of routing messages, so to announce nodes to the network, so E is flooding, here I am, and I receive this information on multiple paths, and we can add information to those messages, which are updated in between, and they act as an indicator for the path quality. So this is the reverse path. And we did that. So here I'm just focusing on this path, but this is a broadcast thing. but consider it here as unicast because it's way too complex to explain it in a broadcast. So what we did is we extend those routing messages, which are used by the Batman protocol, with position data. So each node is using its own position, and it's predicting its own position. And then we add a score. And when E generates this message, it sets the score of the message to the maximum value, which is 1 here. This is then broadcasted, and you see C received this message here. And what it does is C calculates a score of the link to E, to its neighbor, which is based upon the distance and the current predicted distance. So we're making a statement about how is the path quality in the future evolving. And then the received score is multiplied with the score of the link. And C sets its own position values there and forwards the message. This, which is then received by B, and the same principle applies. B calculates the link score to C and multiplies it with the received score and broadcasts it. And then A receives the message which contains a numeric value, the score here, to E. And as I said, there are multiple rules. There will be multiple path scores, and A is then able to make a statement which is my best forward. So the whole thing which I have presented so far is implemented as an extension to the OMNeT managed framework. We are also implementing it for the basic OMNeT at the moment. And we took the moving mobility base model, which takes care about the update stuff of mobility. So you just say, I want my mobility model to update each 100 milliseconds, and use it with the proposed Reynolds model. And then there's a central location service in each node, and the mobility updates the information and pushes the mobility data there. And on the routing layer, the routing protocol receives information from other nodes, like positions, and it's also updating that into the location service. But it can also access the location service and then use this prediction method. So all these things are OMNeT modules. So let's take a look at a quick evaluation. I'm not going to discuss the parameters here, but it's more or less the scenario from the beginning. We have a number of nodes which move here randomly, but not with a random waypoint model. We call it controlled waypoint, but keep in mind we want to predict. We say this is random waypoint, but we know which waypoints will appear in the future. So like a path which was planned before. And then we have a video streaming, and what we evaluate is the video stream PDR to the base station. And we want to find out which approach, predictive path planning and stick merge, is better here, and what's the influence of different channel models. So we use the Fries model as a very basic evaluation, and the Nakayama model to take the influence of packet loss into account. And for predictive path planning, you see here that there is a benefit to bare OLSR. So on the x-axis, you see the prediction width. So what's the benefit from prediction? And but you also see that these curves have different shapes, and this is not a good thing because it means here we have quite a huge influence of the channel. So what you see here is for the Fries model, there's quite a huge gain, but then there's some drop, and it even drops beyond the point where we have no prediction. So this is not so good at all. And why is this so? It's because, as I said, OLSR requires mobility data from all participants. And if there's packet loss, then we make false predictions because we don't have the current data. Now let's take a look at web mobile, and you see here the curves look very similar. There's some sort of offset, but that's related to the channel model. And we always have a gain through prediction. We are not falling to the point where we are less than with the prediction. This means we have a really low dependency on the channel conditions. And this is because every message which arrives at our destination contains the path score, which indicates a value for the whole path. And we have quite a small overhead because every node is doing the prediction for itself and then broadcasts the results and not the individual rare data. So you can see that this approach is performing much better here. Okay, for the conclusion, I've shown the Reynolds mobility model, which uses steerings to model mobility algorithms, and a locomotion layer as an abstraction for different types of vehicles. I've presented the trajectory prediction method, which makes use of this kind of information, and then two different approaches, and we have seen that predictive path planning is only a good candidate if we have very few packet losses in the network. And for the future, we want to extend it. We have another framework which is based on MATLAB, which has a lot of mobility algorithms in terms of cooperative agents, and what we want to do is port them to OMNeT. And we want to extend it with further mobility classes, for example, planes, unmanned ground vehicles, and stuff like that. And of course, our main aim is we want more routing protocols. So we want people to use this to develop new routing protocols, And we are also considering a real-world implementation. And as we have multiple vehicles which are really operating, then test those algorithms with those vehicles. Okay, thanks for your attention.
You have some prediction model, a prediction algorithm for,
Yeah.
say, foresee where a drone will be in the future. At the same time, you have a controlled mobility approach.
Yes.
So the actual direction of the drone will change depending on the position of the others.
Yeah.
Does there have any kind of conflict between the two? Because the actual direction will change depending on what is happening around.
Yeah, of course, this prediction is not a perfect prediction. This is influenced, and then we have some sort of error. Yeah.
Okay. Does it have any influence that the conflict radius you set? So depending on the conflict, I'm just.
This was just an example, but there are multiple things you could think of which changes. Yeah. Yeah, that's a topic of current research. So what we are currently doing is we said, okay, if we have paths which are quite similar, why not use this as some sort of load balancing approach, and then we distribute data on different paths. But so what you have to do is we need some sort of scheduling mechanism, and we need to find a measurement to say, okay, when are they similar enough? Yeah.
Yeah, we're talking about using it as a redundancy.
Yeah, you can also use it
sending the same information via multiple paths, and if one path fails. Yeah,
but you also have to think about if you enlarge the traffic there, then you increase the probability for collisions. This is a trade-off again. Yeah.